So essentially the first part was, essentially we didn't make it to the physics part, but it was about a construction which maps the quantum mass equation one-to-one into a Keldysh functional integral. And in this framework, the structural finding that we could do was to essentially find out simplifications of this Markovian Keldysh action, which consists of a Hamiltonian contribution and this dissipative contribution corresponding to the Hamiltonian dynamics in here, and the dissipative dynamics encoded in this Lindblad generator here. And taking the simplification that the system is placed close to the critical point, we found that this entire functional integral simplifies in such a way that we could actually identify the Langevin equation of motion, which is equivalent to a stochastic driven dissipative Gross-Peter-Ashby equation taken as a semi-phenomenological model describing exocombinarity systems. And in particular, while this part of this story would be the deterministic mean field motion in the presence of temporally inhomogeneous and spatially inhomogeneous fields, this construction also allowed us to get this noise variable in here systematically. So we then asked the question, how can one classify conditions of non-equilibrium physics? And we made the point that essentially whenever you have a time-independent Hamiltonian as a generator of the microscopic dynamics, you would be able to identify the symmetry of this entire Keldysh action here, which is placed down here, and which has really two crucial implications. The first implication of that symmetry, and that is why we are saying that the symmetry describes exactly equilibrium conditions, is essentially the word identity as the invariance of any correlation function under the symmetry transformation, and which yields fluctuation dissipation theorems, thermal fluctuation dissipation theorems. In particular, for example, in the single particle sector, this fluctuation dissipation relation connects the single particle correlation functions, abbreviated with this Keldysh-Green's function GK, describing correlation, single particle correlations, and it relates it to the single particle response of the systems, which is the imaginary part of the retarded Green's function, or in other words, the spectral density of this problem. And the factor in between, that is what qualifies this system here as a thermal equilibrium fluctuation dissipation relation, is exactly the Bose distribution of thermal equilibrium. And the symmetry, if you go to more details, you find that such relations appear in arbitrary order in the correlation functions, so this makes it equivalent to the statement on the entire density matrix and the dynamics equilibrium. So this is really ensuring detailed balance in this functional integral formulation. The second implication of this of the presence of the symmetry can be visualized in a geometric way, and we made the crucial point, which will be guiding us also today, that the equilibrium situation has, based on the presence of the symmetry, a geometric constraint on the location of the couplings of the Keldysh action in the complex plane. So the real part of these vectors here describes all coupling constants that are subsumed in this Hamiltonian contribution to the Keldysh action. The imaginary parts, they correspond to the couplings like a single particle loss rates, two-body loss rate that are encoded in this dissipative part.
So your order identity looks like is it like a Kubo-Martin relation?
It is exactly. So the Kubo-Martin, so you can derive from this symmetry transformation, you can derive this Kubo-Martin Schwinger or vice versa. So it's, so to say, just what I see as a main good point that we formulated in terms of the symmetry is that you just have to look, in order to get information, you just have to look at the action of your problem. So it's a one-line calculation, is the symmetry there or not? While if you go with Kubo-Martin Schwinger, if you take it very seriously, you would have to test the entire hierarchy of correlation functions. So you never stop, because there could always be one that doesn't fulfill it. And so this is a very compact way of saying it, but it's completely correct. As I said, it's a completely equivalent formulation in the functional integral language of this Kukumana triangulation system. Okay, and the big difference between equilibrium and non-equilibrium conditions is this geometric constraint in the complex plane of couplings, which is not present in the driven dissipative systems with the simple physical intuition that the real part of the dynamics, the Hamiltonian dynamics in this problem, has nothing to do, comes from a very different dynamic resource than these dissipative contributions. And now we want to find out some implications of this specific situation. And that brings me to actually the second application. I want to discuss the long wavelength behavior of low-dimensional driven quantum systems. And this program will be along these lines. We're starting from the driven dissipative stochastic cross-beta equation being a valid model for exciton polarity systems. We will decompose the polarity and amplitudes and phase fluctuations, integrate out the fast phase fluctuations, and that will give rise to the Kadar-Paris-Sangh equation. And okay, I split this program into two parts. First, I would like to provide a brief introduction to the physics of the KBC equation, so as it stands here, and then I will make the connection to this exciton polarity resistance and discuss the implications. In particular, what is some of a little fresher result, we'll discuss the fundamental difference of the KBC equation encountered in the driven open quantum systems, where this variable is actually a compact variable phase of the compact condensate, in contrast to the more traditional KBC equation, where this is a non-compact gate variable. So that will be the program for the day. There was a question.
So the semi-classical limit of the function, is it a genetic feature or is it specific to this random?
This is a feature. I mean, as we so say, the logic that I went through was that essentially it becomes a sharp argument if you're close to a condensation threshold, close to a phase transition, then it's really mathematically rigorous that some quantum description in terms of a master equation boils down to the semi-classical approximation. And if we're not exactly very close to a phase transition, still it gives us the useful orientation when the frequencies of interest and probe frequencies of interest are way below the noise level in the system. So that's how I would think about it. Yeah, but so rigorous is only close to a phase transition. However, I mean, it has all the symmetries of the problem, and so it should be a useful approximation. Okay, good. So let's start discussing this KBC equation as it was introduced, so to say, into the literature by Kadar-Paris and Sangh in this famous paper of 1986. So they asked actually the question, well, let's look at ground in motion. Yeah? This is just a diffusion equation with noise. And so this is ground in motion of point particles. And they asked the question, okay, what if we would replace point particles by extended objects, by surfaces, strings, membranes, whatever. And then they found that for such a situation, there is actually interesting qualitative modification that comes in the presence of drive, which I will argue, which is an entirely geometric effect. And you can see that illustrated here. So the physical situation that we look at, a tilted surface, so there's a gravitational field, that means that the system is really driven, because there's a shear force acting on this growing height. And why is the height growing? So this is this height variable here. It's because you're depositing particles, classical particles at some rate lambda onto the surface. Kadar-Paris made the physical assumption that the growth proceeds in an orthogonal direction to this surface that is growing here, and this occurs, so to say, an increment that goes proportional to time with this rate lambda. Now, looking at the geometry of this problem, we want to ask now questions about the height profile, so about the variable that is really orthogonal to the ground flow, so to say. And the geometry of this problem, this is a cosine h over dx, and here we have this h over dx. tells you that the growth or the change of the height is related to the change of the growth direction in precisely this way. And assuming now that this height growth is small, you end up with this condition. And in particular, you see up on this expansion, you introduce a non-linear change of h with x. Okay, and that tells you that the Brownian motion will now be corrected, which is always present, which will now be corrected by terms which are proportional to lambda. And that is written down here. So the height profile time evolution is generated by some Brownian motion diffusive term plus this geometric contribution that comes from the drive. Okay, and to bring you closer to some of these properties of this KBC equation as quantum-partitions, I guess it is quite useful and intuitive for you to think already at that point of this height variable in terms of a phase variable. Yeah, and then you will recognize actually the symmetries of this KBC equation as very natural properties of transforming phase variables in various ways. And so we introduce, just for the fun of it, just to make this analogy, a complex field variable with some modulus and some phase, and we identify now, we want to think about this height variable now as this phase variable. So and then you'll see the natural phase transformation properties being inherited by this KBC equation. So first thing that you can act on a phase variable is, of course, co-moving or rotating frame transformation, which corresponds here in the phase case to a time local gauge transformation, sending this field here to some different rotating frame. And if you look what this does on the phase, and modulus is unchanged, it just sets it to lambda times adds lambda times t. So therefore, we can always absorb this proportionality or this constant contribution lambda here into a redefinition using this symmetry of the variable h, which means in the phase analogy nothing but moving into a rotating frame. Yeah. So, and you can therefore see that this deposition strength lambda has only a non-trivial effect due to this nonlinear contribution. This you can't integrate. And indeed, if you take a situation where there's no external drive that can really act on the system in this way, that can change the physics of the problem, exert a force, for example, we would choose a flat interface, and then there's just the growth, and the geometry of this situation tells you that this nonlinear contribution will be absent, and you recognize that in this way, okay, this transformation is really nothing but putting your observer exactly on top of this growing interface, and being in this frame, you will not see the growth, of course. Okay, so the second property of this equation up there, you see it only involves derivatives acting on this A variable here. So it is modified as a gapless or scale invariant equation, and this scale invariance is guaranteed by actually global gauge invariance of phase transformations. Yeah? So that is the statement that if I send, so that's of course a question of underlying dynamics, but if I have the situation that this transformation doesn't change the physics action of the problem, then it's just a global shift in phase, and that guarantees that there will not be any mass or gap terms being generated in the RG flow of this equation. And this has, so to say, consequences, namely all correlation functions in this problem will be scaling functions. For example, if you look at this height variance function here, you'll find by analysis that due to the gapless nature of this problem, it's a scaling function here with a universal KBC function with the defined limiting cases. And in particular, this chi is the universal critical exponent. Z is another universal critical exponent, the so-called dynamical critical exponent. This chi variable is called roughness exponent for the reason that when chi is larger than 0, it tells you that this big variance, this function here, will ever grow with distance. So one really looks at how does it change when the correlations when I go to larger and larger distances. If chi is larger than 0, I'm arriving at the so-called rough phase of the KBC turns out to be smaller zero, and in fact, in 3 dimensions, there is a phase transition in this problem, and then this exponent is smaller zero, and the gate variance will shrink. So that means that we are going into a smooth phase in the language of this interface, the dynamics. The third transformation that appears is Galilean invariance. So if you think of Galilean invariance, you can apply it to a complex field. Yeah, time is absolute. The position variable has to be shifted by a velocity times t in Galilean transformation, and that is a phase factor that is picked up in order to ensure invariance of the action under Galilean transformations. So what this means for the phase, well, the argument is replaced as well, and you see here in the exponent this shift of some energy and velocity of momentum times x appearing. So this is a Galilean transformation for this one acting on this KBC equation. One finds indeed that it is the symmetry of this problem. And you see here identifying lambda as 1 over m. This is exactly a transformation. If you go through it quite straightforwardly, see that it's really symmetry of this equation. It doesn't change. So, and this symmetry, looking at the problem from an RG perspective, I will connect the RG flow of the constant of here and this interaction constant. So, let's not go into the details here, but it gives you an interesting exact relation on the sum of this dynamical and the roughness exponent that you can conclude from the Ward identity associated in this case with Galilean invariance. Okay, so what is actually the large-scale physics of this ABC equation? So where do these critical exponents I was pointing out, where do they occur? And you see that if you use the RG procedure, so you coarse grain this problem to larger and larger distances. Actually, in practice, you can do it in momentum space and integrate out momentum shells to derive effectively no momentum description of this problem. And if you do this program for this problem here, you see that there is an RG flow of some combination of the parameters that enter this ABC equation. So just to remind you, this was this nonlinear strength. This is the noise level that we have in this ABC equation, and this is the diffusion coefficient. And this precise combination of parameters is dimensionless. And one sees that actually quite nicely all the flow equations that are in this, all the RG equations that are in this ABC problem can be really summarized in this quite simple differential equation. And if you look at its solution, you find the following thing as a function of dimension in the system. So we find the following thing. Let's start in 3 dimensions. There is a critical point, and if we initialize this G somewhere here below this critical point, then we'll find, okay, we flow essentially by coarse graining to long distances. The long distance physics will be essentially at this nonlinear of this strength being located at 0. And the opposite thing happens if you initialize the system somewhere here, then you will be run up to actually a situation where this coupling constant is very large. So what's the physical interpretation of this situation? When G goes to infinity here, then we run into the so-called rough phase of the problem. So this means remembering that lambda is precisely a measure of the strength of non-equilibrium conditions, in the sense that if I untilt the interface, then there will not be this nonlinear coupling in the problem. This means that if the flow runs up, we are really going into very strong non-equilibrium conditions. While if we are running downwards here, we are essentially approaching an equilibrium situation. And so that is really how you should think about this RG flow. And in particular, if you look at the 2-dimensional situation, and that's why I'm now interested in this low-dimensional KBC physics, you see that if you initialize the system, if you even just weakly perturb it out of equilibrium, you will see the runaway flow, you will reach actually a strong non-equilibrium condition at large distances, although you just perturbed it very weakly out of equilibrium on the microscopic scale. And the same thing is true in 1 dimension. Okay, and so let me put you some flesh on the physical contexts where this equation has occurred. It is, so to say, was introduced to describe this stochastic roughening of surfaces, but in fact it appears really in multiple physical contexts. For example, I think the best data on this critical exponent, they were obtained by looking at the defect growth in liquid crystals, where this gravitational field drive is replaced by an electric field that, so to say, pulls this surface out here. Another example where maybe data are not that extremely good, but at least there's some hints for this KBC dynamics is bacterial colony growth, where of course the drive is the sugar that these bacteria are consuming. Or another example is the burning of, or the spreading of fires. Really, even the forest, the fire spreading is an example of this surface roughening in the dynamics. The drive in this case is, of course, oxygen. Okay, let's make the connection to this exciton polariton system. So, as I was saying, we start from this driven dissipative Gross-Beta-Fc equation here, and we make this phase amplitude decomposition. We then end up with two equations of motion, one for the amplitude, one for the phase. And let me point out what is structurally important about these equations. You realize directly that this amplitude equation turns out to be gapped. And so there is a fast dynamics with the scale denoted here that, so to say, makes this amplitude fluctuation stem out very quickly to the stationary state. That allows us to linearize the fluctuations of this chi field and essentially also integrate it out. Here, assuming that the stationary state of chi is reached way before the stationary state of the theta variable is reached. And if you do this very simple procedure, then you produce actually this rather famous KBC equation where the phase diffusion coefficient and the lambda parameter here are specified in terms of the microscopic parameters that handle this equation. And the one thing that I would like to stress in this messy variables is exactly the form of this lambda parameter. If we are in an equilibrium condition, then I was telling you that all these couplings, the ratio of real over imaginary parts, which is one of these ratios displayed here, they have to lie all on one single ray, or this is a ratio of ratios actually, a ratio of ratios. So that must be unity in the case of equilibrium. And then you see that this cancels out, and this symmetry is really a strong thing. That indeed, if I have equilibrium conditions, I know that this must be 1. So that turns out lambda exactly equals 0. So that means that in equilibrium, we don't have this nonlinearity, and you can really understand this in terms of the symmetry that I was presenting yesterday. While the occurrence that this ratio here is not equal to 1 corresponds to the situation where we have a spread in the complex plane, and that, as I was pointing out, is really a strong indication, a proof of non-equilibrium conditions. And so in this situation, we have a very nice situation where the entire non-equilibrium conditions are lumped into the single parameter, and we can study what this parameter is doing. Okay, let me give you an overview of what the physical implications of this dynamics are in exciton polarity systems. So the first point is that this mapping to a KBC equation is valid in essentially all dimensions. If you want, if we are in a low noise level situation, so well above the threshold where ordering is supposed to come in. However, there is this fundamental difference to the classic, let's maybe not say classical, but classical context of this KBC equation, namely the KBC variable now is compact in contrast to the equilibrium. To the surface roughening context. And we tackled this problem so far with two complementary approaches. The first one neglects the compactness of this variable, so that is really analogous to thinking about spin waves in the low temperature Kosovo-Staulis problem. And this leads to one emergent length scale, which we term KBC length scale L star. We then did more recently a complementary approach where where we don't put in, so to say, the KBZ flow of that variable, but so we neglect the RG flow, but we take quite precisely the compactness of this phase. And that leads to a second emergent landscape in this problem, which we term vortex length here. And the physics question that we now have to ask is which of these scales comes first. So both these scales actually diverge in the limit where lambda goes to 0. So in the equilibrium limit, these scales are both pushed out of the problem. So both are intrinsic non-equilibrium scales in this problem. And our analysis now tells us that in 2 dimensions, this vortex length is actually well below this KBZ length. And that means that we end up with essentially 2 scaling regimes in a single part, let's say, in the correlation, spatial correlation functions of this problem. In the first regime, we see here just this vortex length scale. So this is equilibrium-like scaling behavior, and then it's vortex-like scaling behavior, which I will qualify later on. And in 1 dimension, we find that the situation is exactly reversed. The vortex length is much bigger than the KBZ length. And then in 1 dimension, we will have 3 scaling regimes. One which is equilibrium, one which is KBZ, and then the vortex scaling regime. So that gives us somehow the roadmap of what I want to discuss a bit more. So in 2 dimensions, we have this paradigm of equilibrium statistics in mechanics, just to go from that side. We can't have Bose-Einstein condensation in 2 dimension equilibrium. The correlations instead are decaying, so to say, algebraically, and there is a superfluid response in this system. While, so to say, the low and the high temperature phase are separated by this Postulate-Staudis transition, which goes by unbinding of vortex, anti-vortex pairs. And in the high temperature phase, it's just exponential correlations. So let me remind you how this works. So the algebraic decay in the low temperature phase is due to spin waves, to phonon fluctuations, and you can see that by going for this correlation, for the spatial correlation function of the phase amplitude representation, you have to calculate essentially just a single quadratic correlator, and this correlator actually sees the Green's function of the spin wave action here and gives rise to logarithmic divergence. And this log divergence inserted here in the exponent gives us this argument as well. Okay. The second ingredient is this Postulate-Staudis transition. So this is unbinding of vortex anti-vortex pairs. So here the simple-most picture is a single vortex picture introduced by Postulates and Staudis, which balances essentially deterministic forces acting in the system, I mean energy, interaction energy between the vortices, with entropy, so the statistic effect. So in the low temperature phase, the picture is that these vortices are bound into small pairs, and so at large distances, therefore, there is no field associated to this vortex, because the anti-vortex field will just compensate. The question that they ask now is, when is it favorable in terms of the free energy to unbind these vortices? And to this end, you have to just compute the energy of a single vortex configuration of an unbound vortex, which turns out to have a 1/r velocity profile in this circular direction of the vortex, so that gives a log divergence of the energy of a single vortex. One can then look at the entropy that vortex configurations may have, and if we equally distribute them over the entire 2-dimensional plane, you also get a log over a squared. And balancing this to construct the free energy, you find that these 2 logs, the coefficients, they may compensate, and indeed, at high enough temperature, this entropic effect of placing the free vortices here and there, it wins actually over the energetic, over the deterministic attraction between them, and gives rise to this Postulate-Staudis transition. Okay, now back to this problem that we have. I will go now to the physical implications of this smooth KBZ fluctuations. And here we've already essentially told the story that we are here in 2 dimensions, and the system is initialized at microscopic distances with a weak perturbation out of equilibrium. And then you see that the RG flow will always focus us into this strongly non-equilibrium KBZ phase. And in particular, we will generate, even if we start here very small, we will generate a length scale which is defined by this coupling constant in the KBZ equation here, reaching unity. With the picture being that if I'm here at small g, so it's still a weak equilibrium situation, I only feel the physics of equilibrium somehow, but if I'm way beyond this scale, then I feel strongly the physics of this KBZ equation. And that gives us, so to say, these two scaling regimes in the correlation function. At short distances, we are still at this Oberligovo-Spinway fixed point, where we have an algebraic decay of correlation functions, while in the large distance regime, we are, so to say, close to this KBZ fixed point, and then the KBZ analysis tells us that we are in a rough phase here with this exponent 2 alpha, which gives rise to some exponential decay. And that is then the picture result for this correlation function. Short distances, algebraic scaling, large distance, sub-exponential decay. And so to say, one reason why this evades experimental detection at that point is that this crossover scale is really exponentially large that is placed here. Okay, let me skip maybe the part of superfluid response and rather focus now on the physical implications of the compactness of the phase. Yeah? So in two-dimensional equilibrium situation, there is actually an interesting analogy, direct analogy between vortices and electric charges. So in particular, it's for instance electric charges, they will interact logarithmically and they have 1/r force in between them. And so to say, in this mapping from vortices to electric charges, one encounters actually this dual relation between the dielectric constant and the superfluid stiffness, so the coefficient in this, so the superfluid response in this system. In particular, if we have the superfluid, that is will then be described by the dipole gas in this charge analogy, there we have a dielectric constant which is finite polarizability. However, if we go to the unbound phase of vortices, then, I mean, if you apply an electric field, these charges will immediately go to the borders, and this dielectric constant diverges, meaning that the superfluid stiffness here goes to 0 in that phase. And we now have to ask, or want to ask, how is this scenario modified in the driven system? So this is, at first instance, also in some sense, a mathematical field theoretical problem. We have this KBZ equation here, and since this models now a phase variable, we have to incorporate the phaseness, the compactness of this variable. And how is this expressed? So we have actually a discrete and local gauge invariance in this phase variable. So this phase variable should always be located on an interval from 0 to 2 pi, and we can shift it by any integer at any point in space and time, still recover exactly the same physics because of the origin of this theta as a phase variable. So we have to put in some of this compactness in this way. We have to implement this local gauge invariance. And for the deterministic part, well, that's somehow a standard procedure. One just chooses a lattice regularization and so discretizes these operators, these differential operators, and then in this deterministic part, this gauge invariance is really manifest because it's periodic functions. In particular, it's interesting to note that this somehow innocent-looking thing introduces reference to a short distance scale, the lattice spacing, which somehow can already at that point anticipate it to generate another length scale in the long wavelength behavior. So this short distance scale introduced via this regularization will make its way to another macroscopic scale that we have to expect. Now, also note that in the situation where lambda equals 0, then there exists actually a potential function hxy, xy Hamiltonian, whose derivative actually is exactly this sine function here. So this gives really this typical cosine xy Hamiltonian, And in this circumstance, by mapping, for example, the Fokker-Planck equation, one can immediately read off that there's a Gibbs ensemble stationary distribution, which is of this type. When lambda is non-zero, then you can find potential function. This is another way of indicating non-equilibrium conditions for real variables, and you cannot immediately write down the statistical distribution. Now, the second point that we have to make sure is now to work on the discretization or the implementing the phase discrete phase invariance of this time derivative term. And to this end, we realize actually that the phase may do discontinuous jumps, so we shouldn't think of it in first place actually as a differential operator. In the end, we do a sequence of manipulation that will allow to do so again. But in principle, we have to think of it now as a stochastic update here, which on a time epsilon can make a huge jump. Namely, if our phase is 2 pi minus epsilon, and we add a little in the next time step, we add a little more, then we add here actually this entire integer, 2 pi, and bring back the variable this way to the interval 0 to 2 pi. So this is, so to say, our way of implementing gauge invariance in the time derivative here. And then, if you take this through the mathematical machinery, you can see actually that the stochastic difference equation that we have here maps into a discrete dynamical function integral. So that's an interesting situation that I also didn't see before, that this summation, this continuous noise variable summation that we encountered yesterday in this dynamical function integrals is now replaced by a sum over all possible configurations of choosing this discrete variable n of t and x. So this is described here. Now there's then a few steps, and maybe I remove this black box into a gray box, but I would agree that it's maybe not the ideal thing of explaining. Mainly we can just track the variables that appear in this problem. So we have here a function which is periodic in this variable here, so it's theta and tilde, and these two variables theta and tilde are replaced by source variables j and j tilde. For this j and j tilde sources, we find a continuity equation which allows to resolve this continuity equation in terms of gauge fields actually. So we have here, if you want, emergent gauge fields that work, but they come really from a physical constraint that these two newly introduced variables have. And maybe this is details, but just look how this sum, how this functional integral that we started with has transformed. We have now variables phi tilde, so this is like an electric potential, and we have a vector potential and its noise conjugate variable here. Now we don't like to work with the sum over discrete variables, and that's the reason why we do here another manipulation, which is a so-called Poisson summation formula, with which you can always transform a weakly or badly convergent sum over integers into an integral and a little summation over integers, where however you can hope that this summation truncates after the first two so the summation terms. And so this is a standard way of moving from some ill-defined or weakly convergent sum of integers into integrals and a little bit of summation over the variables. And that brings us now to a form which at least has a clear physical interpretation. This functional integral here is essentially an electrodynamic gauge theory for an electric potential and a vector potential here, which are smooth fields. And we also have in addition summation over discrete variables which represent the vortices and the vortex currents as well. And we can interpret this result here actually much better if we go back now from the function integral to the Langevin equation description that we looked at yesterday. So the Langevin equations that are associated to this function integral are actually modified noisy Maxwell equations. If we replace our electric and vector potentials in terms of electric and magnetic fields, we find these equations of motion here. And they're really reminiscent of classical electrodynamics in the presence of noise. So the first point here is we get this irrotational flow here, so this Poisson equation for the electric field here, we get this Ampere law here, where the time derivative acting on the magnetic field that you have usually in electrodynamics is replaced by an overdamping term. So there's no time derivative acting here. The Ampere law here is replaced by this expression, and in particular you see here systematically appearing these source variables, these discrete variables, which came out of our construction, which can be interpreted really as charges, as I was promising in the beginning. So these are vortex charges, these discrete numbers here, they give rise to the sources for this electromagnetic fields, and there's also vortex currents in the game. Now, in addition, we supplement this with the dynamics for these vortices, which are moving, so to say, from the electric field. And we can now get intuition on these equations by actually making the identification of the fluctuations of the density in this problem as the magnetic field and the gradient of the phase in terms of the electric field. So if we insert these conditions here, and in addition integrate out this gapped density fluctuations, so the gapped magnetic field variable that we have, then we end up with an equation that is of this type, and you can recognize quite easily the structure of the KBC equation. So think of this electric field as a gradient of the phase. So this is, so we can pull that out. So this is the time evolution of the phase. Here is the phase diffusion, and here you recognize this electric field square term, which is nothing but the phase gradient square that appeared in the KBC equation. So so this happens if, in addition, we neglect these vortex charges in addition. So we reproduce quite nicely this this limit of the smooth KBC equation in this formulation. And notice also that the electrodynamic that we are deriving here is a nonlinear electrodynamics, unlike the typical Maxwell equation, because of this quadratic appearance of the electric field in the equation of motion. Okay, so the next step of this analysis is actually to integrate out the smooth electric field fluctuation and construct an effective theory for this vortex increase of freedom. So this amounts to calculating the two-body interaction potential between these vortices. And it turns out, if you do this in the limit lambda equals 0, in the equilibrium limit, then you reproduce this well-known result of a logarithmically divergent interaction potential between these two vortices here. So this reproduces the equilibrium conditions. Now we have this nonlinear term in the electric field, so in the non-equilibrium case we can actually integrate out this electric field exactly, but we can do it perturbatively. And if we do so, we found the following result. This vortex, the vortex interaction potential is actually corrected by this log cube contribution. This is the dominant one. So, and you see that it's really directly proportional to the non-equilibrium condition in the system. And that means actually, physically, that whenever you separate these vortex pairs by a distance beyond this hump, beyond this maximum in the potential, they will actually go away from each other in a fully deterministic way, other than in the equilibrium case, where they could only be separated, this log potential could only be overcome by an entropic effect. And so we must now expect that even at, so to say, zero or low noise level, if you tear these guys far apart from each other, then you will see this vortex unbinding, you will see a vortex unbinding. And the length scale here is even here exponentially. So we can also study, and I finished that, the modification of the Kosterlitz-Thouless flow equations. So in equilibrium we don't have these extra terms, and we see a clear phase transition, the Kosterlitz-Thouless transition, and here the dielectric constant of the superfluid stiffness go to a finite value at the KB Kosterlitz-Thouless transition point. The system does this runaway here, and this is now modified under non-equilibrium conditions where we lose essentially the regime where we have this this fixed superfluid stiffness, but will always essentially at very long distances unbind these vortices and run to a phase without vortices. Okay, let me, I think, skip this here and summarize. Okay, I only made it to these two-dimensional examples. So we have two emergent length scales obtained in these complementary approaches, this KBC length and the vortex length. And so to say, because we find that this vortex length is always for exciton polarity parameters, is always really smaller than the KBC length, and that this scaling of equilibrium will not be cut off by, there will be not a subsequent KBC regime, but rather this vortex regime, which is characterized by exponential correlations. And in one dimension, the situation is exactly opposite. So in one dimension, we find actually temporal correlations, that we have an equilibrium scaling regime, there's a KBC scaling regime, then the scaling of this KBC scale is much more favorable in this case, and that only then we find in one dimension a regime with exponential correlations, which can be actually understood as an unbinding of space-time vortex defects. So we're in one dimension, we have one spatial dimension, one temporal direction, and it's possible to have, so to say, vortices in the space-time, and they can also unbind, and they give rise actually to yet another scale, which will sit on top of this KBC behavior in the very asymptotic long-distance behavior. But there is a potential to observe KBC scaling in these one-dimensional systems. Okay, sorry. Thank you for your attention.
Okay, so we already have some questions. Are there any more questions?
Here you mentioned that your vortexes has close analogies with the charged particles. Can you model dipole particles with the vortexes?
Well, I mean, a vortex pair
Vortex pair.
is a dipole. So it's charge plus minus 1. And so, yeah, that is really the picture. And so, and the analogy in equilibrium is really that you have this 1 over r forces acting between them, or logarithmic potential.
And we can reproduce, for example, dipole-dipole interaction potential between two pairs of vortexes.
That's exactly the approach. Yeah? We compute the non-equilibrium correction to the vortex-vortex interaction potential. And it turns out that we have this log cube behavior with opposite sign. So it's becoming a repulsive potential at large distances. This is the main non-equilibrium effect that we have.
And this is in quantum picture.
This is it?
Is it a quantum case or classical?
Well, yeah, so I would say, I mean, the equations, these are semi-classical Langevin equations, so I see that this is the classical.
Classical.
Right, so yeah, you mean there's of course work, so to say, on exactly zero temperature, vortex unbinding, and so, but there you can map it to this classical statistical problem in one more dimension. And that's actually what we can also do here. So in this 1 plus 1 dimensional space-time picture.